Hello, people. This video is intended to help you with the uncertainties for our constant velocity lab. As you can see here, I have a position time graph. It is scaled properly because it takes up 2/3 of the graphing space, both vertically and horizontally. The trend lines do not connect all the dots. There's kind of the same amount of missing above and below the dots approximately. The trend lines are drawn with a straight line. They are not forced through 0, 0. I have chosen 2 points on each line. As you can see in the purple line, I've got it right here. This spot right here, this one, okay, where it crosses the grid. I'm not choosing data points. Repeat, not choosing data points. I'm choosing points along the trend line where the grid crosses. I'm choosing data points that are far apart. If you choose like, aren't these far apart? No, those are not far apart, silly. What are you doing? Far apart as possible. If you happen to draw a line that's like 45 degrees and never really goes through any grid crossings, then I don't know what to tell you. You just got to do a better job, or come see me and we'll work something out. No big deal. Anyway, I have calculated the slope of both right here. Okay. Notice I have used units in my calculations, not just the answers. And yeah, these are the data points that I've chosen. For example, the blue one here is at 2 meters. This location here is at 2 meters at 8.33 seconds. Excuse me. And the other one at the bottom there is around 0.6 meters at 2.67 seconds. And I've calculated the slope for each. Now, let's assume after you've done your uncertainties that timing is your biggest uncertainty. A timing uncertainty would be plus or minus 1/10 of a second. Okay, that is our uncertainty for this particular lab. It will be different for other labs. We discussed in class how if you were to add 1/10 of a second, and I'm exaggerating here, to each of these data points, it wouldn't change the slope of our line. And if we subtracted from each, it wouldn't. So what we want to do is we want to add to one of them and subtract from, the other. So this is what it looks like. If I add 1/10 of a second here, now the data point has shifted. I realize this is way more than 1/10. I'm exaggerating. And I'm going to subtract 1/10 of a second from this one, and that moves it here. Now my line, which should be drawn with a straight edge, looks something like that with steeper slope. So I've made that one smaller slope. I could, if I wanted to, I could do, for this one, I could subtract 1/10 of a second. Again, this is just trying to help you visualize it from this data point and add to this data point. And now look, my slope is steeper. So I've changed the slope of each line. That's what it would look like graphically. You do not need to do this. You need to do it mathematically. I'm just trying to give you a visual representation of it so you can see why we're adding to one and subtracting from the other. If we go down to my lovely math here, you can see that for the stuff that's written in the black ink, I guess you could say, in the black color, in the denominator, I have added 1/10 of a second to the 8.33 and subtracted 1/10 of a second from the 2.33 and redone my calculation. I have shown the work. I've used units in my work, and you can see that the slope has changed from 0.467 to 0.452. So I have decreased the speed based on the uncertainty in our timing. As for the other one, you could see that I subtracted 1/10 of a second here. I've added 1/10 of a second there. As with the picture, that would increase the slope, and it went from 2.47 to 2.56. Again, the purpose of doing this is because our biggest uncertainty is 1/10 of a second. How does that affect the trend line that we draw and the slope that we calculate? That's what we're doing. I just decided to make one of them bigger and one of them smaller. You're welcome to do the same. Now for the challenge. Later in your lab, you are asked to use this adjusted slope to regraph and predict using a graph where the two cars will meet. All right, so here we go. I originally had that these would meet somewhere around 1.31 meters in about 2.8 seconds based on my graph. And here we go. Come on, buddy. Come on. This will not be edited, but for some reason it's not letting me scroll down. And my pen stopped working. There it goes. Sorry. This will not be edited. So let's say the faster car is going to the right. Its new slope is 0.452. This is what I'm going to do. I'm going to go to 1 second, and I'm going to go to approximately 0.452, which is right there. Yes, I could say it starts at 0, 0. And I'm just going to draw a line with slope of 0.452 as best I can using a straight edge, which is an envelope in my hand right now. Not too shabby. Okay. Technically, I shouldn't go off the graph, but I did. The other car is starting at 2 meters with a slope of 0.256. Okay. So I'm going to go over a second, and I'm going to go down 0.256. Oh, boy. Where are we? Give me a different color here. You're my boy, blue. And 0.256. It looks to be, I mean, like maybe there I'm talking. Like, I don't know. And we'll start it at 2. Now I know I'm drawing a line with a slope of 0.256 as best I can with a straight edge. It's not going to, it's not going to be perfect. Okay, not perfect. Yippee! I did it. All right. So what I just did was I regraphed the velocities of the two vehicles based on the largest uncertainty and used the graph to predict where and when will they meet. Well, here's my new data point. Right there. That's where and when they're going to meet. It looks like they are meeting at 1.40 meters at a time of, I don't know, 2.67 seconds? I don't know. It doesn't have to be perfect. You think I'm going to look at every one of your labs and be like, nope, should have been 2.66. I have a life, people. But remember, the original answer that I predicted with my graph was somewhere around 1.3 meters and 2.8 seconds. Based on the uncertainty, maybe they could have met at 1.4 meters in 2.67 seconds because there's uncertainty in our timing. And that's the whole point. How does that affect our results? Okay? And that's the part of the lab where you're asked to regraph. Now, some of you may have had that measurement uncertainty or sliding of the packets was the biggest uncertainty, more than 10%, which was your timing uncertainty. Okay, no big deal. Here's my original calculations at the bottom here. Boop, boop. I just copy pasted from above. Let's say that I said the biggest uncertainty was mismeasuring by plus or minus 0.04 meters, and maybe I had some intervals that were small, so that made it more of a 10% error. Notice what I did here. Same thing, plus or minus. So for the first one, I added plus 0.04 meters. And for the second one, I subtracted 0.04 meters and got a steeper slope of 0.48. Yeah, 0.48 is steeper than 0.467. For the second one, I subtracted 0.04 meters to the first number and added to the second. And in doing so, I decreased the slope significantly. Wow, I hope that math is correct. But I've changed the slope. Then I would use those slopes right here, these two slopes, 1, 2. Go back up to, there's a part in your lab where you're asked to predict with a graph, and I would do exactly what I did here, but with your distance intervals. So anyway, I hope this video has been helpful. It's the first one I've done in a while. I'd still give it roughly 3 out of 5 stars, and I highly doubt I would change anything about it.